possible for somebody to think of that you can transmit anything. Now you can, now it's just a simple thing. You can go for streaming software and stream it through whether it is Facebook like thing or YouTube channels or whatever, you can stream it immediately, right? So that is the way, the communication has changed in the recent years. And with this pandemic situation had made it to learn everybody more and more, and now everybody is having the tool, and now we are demanding more. As I said, that we are looking for whether we really want to feel of the person. It should be, it should not be just like the 2D movies, 2D things. It could be the 3D reality of the same size you can create for somebody. And I know there are many companies which are already using this AR and VRs for this purpose, their purposes. And it's not only that you see, the artificial intelligence is being used even in this your personalized requirement of the personalized requirements, personalized content, and so on. That is also possible through using the AIs. And so I, as you also see that it all has been possible due to the high speed communication, and I will say the high quality of the pictures, whether it is 2D or 3D, it's all has been a result of, the research being done in this field, that is photonics and communication. And these are the important field for today's, and I hope that something good will come out of this faculty development program, and our faculty, those who are participating in this program, and will learn a lot of new things, and they will be able to transmit that to their students, or they will be able to learn their things for their research purposes. So I wish great success to this faculty development program, and I congratulate the Department of Physics, Professor Devendra Mohan, Sujata Sanghi, and other colleagues, those who are taking the initiative, and those who have participating in this event. So thank you very much. Jai Hind, Jai Bharat.
Thank you very much, sir. Thank you for the motivational words. You have rightly said that virtuality has become the reality nowadays. And
Yeah.
as you know that necessity is the mother of invention. So we are looking for the various problems to solve. And as earlier it was said that laser is a solution in search of problem. Today I would say that photonics is a solution in search of a problem. If there is any problem, photonics has a solution for it. So optical communication and high-speed communication is the day of the need, and we have the solution through photonics. So with these words, I once again thank you very much for joining us and giving your blessing words. And now I would like to invite Dr. Noor Hafiza from UTM, Malaysia, to say a few words on this event. And I invite Noor Hafiza to say a few words.
Okay, hi everyone. Hello, everyone can hear me, right? Okay, hello and good morning everyone. I'm really honored to be a part of this FDP on recent advance in photonics and communication conducted by GJU, Science and Technology. And I'm Dr. Hafiza binti Hasim from Faculty of Science, Department of Physics, University of Technology, Malaysia. And I would like, first of all, I would like to congratulate GJU for establish itself on world level academic platform by securing a rank band in Times University ranking for 2021. Earlier this year, the memorandum of understanding between UTM and also GJU has been sealed. And as for introduction, here in UTM, Faculty of Science, there are 4 departments, which is physics, bioscience, mathematical science, and also chemistry. And here we are under the group of Advanced Optical Materials Research Group, AMRG, from Department of Physics, leads by Dr. Eza Shuhada. And here in MRG, we done lots of research, and and the area are in glass synthesis and characterization, optical crystal growth and characterization, linear and non-linear optical properties, solid state laser materials, and nanomaterial analysis using analytical techniques, electronics and optical properties, plasmonic nanoglass, semiconductor nanostructures, nanocrystalline solids and ceramics, thin films and also nanotechnology, metamaterials, and also thin film based solar cell. And here a lot of research have done and lots of students also in here. Previously on 21st September 2020, we already embarked our first collaboration activities between GJU and UTM, where we done a webinar on the novel optical materials for 21st century. And this webinar is under the online global classroom done by the Faculty of Science, where right now we are impacted by the COVID-19. So this online global classroom is very good, as we can actually connect with each other through online. So it's very good for everyone to share their knowledge, as even though that we are far away, but through online it can be useful for all the students and also the staff surrounding. And then it was indeed a fruitful collaborative program which gives insight of the future optical materials, which can be useful for a wide range of applications, such as photonics. This OGC, Online Global Classroom, saw a total of 185 participants from 8 different countries, such as Malaysia, India, from Turkey, and then China, Nigeria. And there's lots of undergraduate students also participate, which is 107 students, and 40 of them, the other 40 are from postgraduate students, while they are staff, and also it consists of 16 different universities around the world. And this will be a start of our collaboration activities, and hopefully we can get more of it as we can do more collaborative activities, such as joint conferences, seminars, and everything. And here in RMRG, Faculty of Science, Department of Physics, we are open for more collaboration in the future in many research area also, because just in our groups, there's a lot of different type of research area, and we also do a computational analysis too right now, and also experimental analysis. And thank you for the GJU for invited me and let this FDP of the recent advances in photonics and communication be very successful event. And hopefully all the students and staff who are joining us could get the glimpse of everything, and we use it for our future advances in research. And yeah, it can give us a lot of new knowledge too. And thank you again, and a very good day to all of you. And hopefully this event will be a very successful event. That's all.
Thank you very much, Dr. Nur Hafiza, and you have very well said that our relationship will go ahead with the area of photonics. Particularly, you have narrated all the fields where we can collaborate, and our faculty and research scholars can even visit you as well, and your faculty and research scholars can visit us, and this will be a beginning. And we will be having more and more events like this. Lastly, I was the speaker for UTM, last month. You had a webinar on that, and we will go ahead with this series of webinars. Thank you very much. So now may I request Professor Sujata Sanghi to make vote of thanks.
Thank you. Thank you, Professor Devendra Mohan. Hope I'm audible to all. A very good morning. A very good morning to all present in this Atal AICT, Atal FDP Faculty Development Program of AICT Academy. The theme of the program is Recent Advances in Photonics and Communication, which is being organized by Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar. So I'm very much thankful on behalf of my department as well as on my own behalf, and extend my sincere thanks to our chief guest, Professor Tankeshwar Kumar, who has graced this function by his presence and has spared valuable time. He is always extending all support for organizing of this faculty development program online. Thank you, sir. I must tell that under the dynamic leadership of our Vice Chancellor, University has evolved academically and has achieved very new milestone at international level. As Professor Devendra Mohan told that recently, Guru Jambheshwar University has been ranked in the band of 801 to 1000 in Times World University Ranking 2021. And this is a great achievement by the university under his leadership. And also, not only this, in the subject ranking of physical sciences, university has secured the band between 601 to 800 in Times ranking 2021. So really all these efforts under his dynamic leadership are appreciable, and we are hopeful that we will be getting all his support. Thank you, sir, for your kind support and guidance at every step for upgradation in all directions. We are also thankful to the to Professor Noor Hafiza Hasin from University of Malaysia for gracing the inaugural function by her presence. Definitely, she has played a very active and important role in getting the MOU between University of Malaysia and GJUST. And I am hopeful that there will be very good exchange between the academic exchange between the staff and the students, research scholars in the department at both the places. Thank you very much, madam, for your support and motivation. We are also very much thankful to AICTE for identifying Department of Physics, Guru Jambheshwar University for grant of the FDP, the financial assistance for organization of this FDP in Photonics area. I must tell that there are around 465 FDPs which are being sanctioned by AICTE all over the country. And in Haryana, around eight FDPs are sanctioned, and ours is the one among all those eight FDPs. So definitely it is a matter of pride that we are having recognition at state level from AICTE. So we are also thankful because AICTE chairperson recently visited our university, and we are thankful to AICTE, the whole staff, for identifying GJU for this FDP. I'm really thankful to Professor Devendra Mohan, who is the coordinator of this faculty development program. So he has taken all the pains. I must tell you that he was busy since the applying of this FDP as well as after the sanction of this FDP. He has taken all the pains for organization of this FDP. So Professor Devendra Mohan, I really thank for your dedication and zeal and interest for this organization of FDP. As told by the coordinator that we are having internationally renowned speakers from India and abroad who will be delivering lectures and interacting with the participants during various sessions which are spread over the 5 days. That is starting from today, it will be up to 6th of November. And I'm thankful to all the speakers and the resource persons for their contribution in this FDP. And I'm hopeful that all the participants from various parts of the country who are attending this FDP, they will be highly benefited by their experience, expertise, and will definitely continue and go for looking for new areas in the photonics and pursue their research in this photonics area. So I'm really thankful to each one and everyone who is present in the program. Have a good day. Thank you. Thank you very much. Thank you, sir.
Thank you, Professor Sujata, for the nice words. And Dr. Gopal Hegde has joined us. I welcome him. And immediately after this inaugural ceremony, his talk will be starting. And before that, we will go for national anthem. so everybody can stand up at their seats where they are, and national anthem will go on.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you everyone. And now immediately after this inauguration ceremony, we will be starting the lecture. Dr. Gopal Hegde is with us, and let me read out the brief. Yes, Dr. Gopal Hegde received his MSc and PhD in physics. He is currently faculty with Biosystems, Science Engineering and Aerospace Engineering, Indian Institute of Science, Bangalore. He was an associate professor in UK, Open University, Singapore, and research director at the NPAEM Center of Innovation, Singapore. He has over 180 publications in international journals and conference proceedings and has filed 6 patents. He has guided many MTech and PhD students. He taught various courses on photonics, semiconductor physics, electronics, mathematical modeling, engineering materials, etc. at undergraduate, graduate, and PhD levels. He has presented invited talks, keynotes at various institutions and at national international conferences. He has been advisory, review organizing member of many international and national conferences and a reviewer for many international journals. He has completed many sponsored research projects in India and Singapore. He was a consultant to many industries in Singapore. He was visiting professor in the FEMTO-ST Institute, Université de France, Comté, France, University of Rennes, France, University of California, LA, USA, and La Trobe University, Australia. His current research interests are in the area of photonics, optical sensors, integrated optics, optical flow visualization, photovoltaics, biophotonics, nanofabrication, and microfluids. He is multi-talented as Hindustani music accomplished and Yakshagana artist and a progressive farmer. Oh, thank you very much, sir. I now remember that you were having a good musical program at your place when we were together. So,
yeah.
so
Can you?
it is a rare combination. Dr. C.V. Raman was also a great guitarist.
No.
So,
okay.
So by welcoming Dr. Hegde, let us welcome Dr. Hegde and request him to present his talk now.
Okay. Good morning to everybody. Can you hear me?
Yes.
Hello.
Yeah, sure, sir. Sure, sir.
Okay.
You
okay,
are
good.
very much audible.
Please carry on, sir.
Yeah, this is the worldwide problem. We will not be able to see, but still we have to talk. Okay. I will share my slides. Okay. One minute. Where I have to share? Input is not required now. Hello, where I have to share my slides? Hello. Hello.
Okay. I am stopping my sharing.
Okay. You have to stop.
Yes, I have stopped.
Okay. Now I'm. Okay.
Okay.
Are you able to see my slides now? Hello.
No, sir, it's still not.
Yes, I am trying to get. Just hold on. I'll let you.
Yeah, somebody has to come out.
Hello.
Hello.
Yes, sir. You just see the a button present now and then select entire window, sir. When you will click on this present now, you will
Yeah,
get.
I already clicked.
So you have to click on entire screen.
Yeah, that's what I did.
And
Not coming. Share your entire screen. Okay, that is there already. I am able to see that. Hopefully now it will come.
Yes, it came.
Now, can you see my slides?
When you click on the slide, we are able to see the slides. So you just go to the presentation mode, sir.
Okay.
You will able to see it.
You are presenting. Okay.
Click on the slide, not the Google one.
Yeah, I already clicked. Okay.
Yes.
Yeah, now it's visible, sir.
Okay.
Now it's visible.
Yes.
Yes, sir.
These are visible.
Now?
Yeah.
Good. Can you see? Okay.
Yes.
Yeah. Let us start. Okay.
Yeah, start, please.
So it's my pleasure to show. I am from some remote place in Karnataka. This is my school somewhere. Okay. I'm from this Western Ghats area. Okay. Beautiful, colorful pictures. Where I come from. Falls around in Karnataka. Okay. There's a world famous Joke Falls. Can you hear me now? Is it okay?
Yes, okay. Yes, I can hear you.
Sir. Yeah. So this is the world famous waterfalls near my house. Okay, this is the way of life over there. Okay. Okay, I'm call the talk. Hello. This is the art I talked about. Yakshagana. Okay, now let me start. At a glance, I put the title as at a glance. That will be more suitable. That's okay. And whole of my talk is planned in such a way that at a glance, what is nanophotonics? In brief, many of you are now working this field. Then nano fabrication a bit, because that is very important to do nanophotonics. Then I will give you some of the devices of microphotonics, so that it will give a foundation for nanophotonics or nano fabrication, micro, nano, and I will also show some of our work in the area of nanophotonics. That's how I planned this talk. So before going to nano photonics, actually, let us get an idea of what is nano. I think you know, but I don't know the background of all the participants. I assume that there are some students as well, such as faculties. Since it is an online talk, we will not be able to see who the participants are. So I have to cater for all types of participants, hoping that students are also sitting. Let me give a brief idea of what is the nano. The dimension is scaling, I think you all know. So ultimate goal is to achieve the dimension of an atom. That's what the scientists have been trying. Then do a lot of try to understand the physics behind the nanostructures and try to explore the applications. And that's what the whole objective of this micro nano whatever it's called. So this ultimate dimension that is 0.1 nanometer. Okay, a generic. This is like not atom image. That is just a theoretical model, one image of that model. That's one angstrom. That's ultimate goal. And if you look at this one, this is where the actual nano started. That's the graphene and the nanotube. Okay, nano ribbon is a sheet of carbon atom thickness is about 1 nanometer. If you look at the the single wall nanotube, the same sheet is rolled into a sheet that is about 10 nanometer. And this is a multi-wall nanotube that we are talking about 100 nanometer. It's where the technology stands somewhere in between 10 nanometer and 100 nanometer. And that's what the nanoelectronics is talking about. Then see, this is okay for the same thing. You can do all sorts of sheets into multi single one, multi-one. And if you look at this, is where other fields where nano is more multidisciplinary. If you look at this one, then nano rods is more talked about other type of nanostructures. That is fabricated chemicals methods. Can you hear me? Is that okay?
Excuse me, sir. Yeah, your voice is disturbing, sir. There is
Now?
in your voice.
Now?
Voice is
Hello?
disturbing.
Now?
Hello, sir. Now it is okay now.
Hello. 1 minute.
Yes, sir. It is okay now.
It is okay. 1 minute. I'll switch off the fan. Hopefully. Now it's okay. If you look at the the right side image is I'm just giving the scaling down. This is ZN and nano rods of 1 microns. So some of our work only. We use this one for some application in electronics and photovoltaics. And the next one is a human red blood cells that is about 10 to 15 microns. And this is one of the important things in MEMS, micro electromechanical system. Tweezers can pick up and move individual cells that is controlled to electronics and mechanical in that's all MEMS. That is about these are all well established devices now. Size is about 100 to 150 microns. Okay, so if you look at the carbon nanotubes or carbon, this is the dimension which I mentioned about 10 to 100 nanometer. And very important thing is the size dependent fluorescence. And I on the left side I put this is commercially available now. Okay, lot of techniques have been developed, and this in India also can find this carbon nanotubes commercially available. And if you look at the right image, right side, you can see the size dependent fluorescence. That's where the nanophotonics idea is started from that point. And this is very, very interesting. Okay, the basic properties, the whole idea is when you reduce the dimension of the materials, You see a lot of physical, chemical, biological effects, biology and electrical, electronics, optical properties change. That is where the new ideas are started coming. That is the important thing here is the multidisciplinary activities. That is where nanophotonics or nanotechnology is known for. So this is how the idea started. If you look at some examples of micro and nanotechnology, this is where MEMS based gear system. And this was, I think I saw this one around 22 years back in UCLA when I visited there. They demonstrated this MEMS-based gear system. It's a very independent device. They demonstrated the movement of the entire gear system. This is where MEMS, this is 22, 24 years back. This is now the current state of the art. Okay, and the NEMS, nano electromechanical systems based gear system. This, you see, this is not the real one. The left one is already realized. The right one is, it is just a simulation. Okay, simulated with 15,500 atoms with a parallel shaft spirit reducer gear is one of the largest nano mechanical device ever modeled in atomic scale. And this is the ultimate goal. I think one day we may realize these structures. And if you look at this structure, okay, sorry, I think there are some Kannada words still sitting there. Okay, I used to give this talk in Kannada as well, just introduction. So here, if you take the light interaction with matter, so when the light enters any material, there is one of these phenomena will happen. So one is scattering, either a reflection or a refraction, absorption by the material, and the transmission. This is where this is known for ages. This is called the bulk optics, or interaction of light with bulk materials. So, and you see each of this scattering, if you know, that's what the Raman spectroscopy is entirely based on the scattering, the reflection, the refraction. This is, everything has a application. A lot of the studies have been made on this one. The spectroscopy depends on this one. This is absorption spectroscopy, transmission. So this is bulk, but a lot of things have been developed over the years. Now this one, okay, still continues. I am not telling that one, okay. And same thing, light matter interaction at nanoscale. This is the difference. The interaction of light with bulk materials, interaction of light with micron scale material or the molecules, atoms, and the nanoscale. This is entirely a different thing. Okay, some of the images I have shown here. So this is the quantum dot, and this is pick of feather. That also you see some nanophotonics, and this is where the photonic crystal, the right corner at the bottom, and we see on the right top corner, left right corner, that is the rainbow effect. That's what the scattering or the Raman effect was realized, and this is where the nanotechnology in Roman times. So that time they were not knowing this. Nanostructures there. They are making powders of gold and silver, and they used to put inside or paint it within the cup. Okay, Lycurgus cup, like Lycurgus cup. So they, when the light inside changes depending upon the dimension of the coated nanomaterial, they used to see different color. That's what they were not knowing it's nano, but they used to do. It was there for ages. No, nanophotonics was a lot of things in light matter interaction like nanostructures, quantum dots, plasmonics, photonic crystal, metamaterials, application of the structures for nano. That is all things which covers the nanophotonics. Now, see, this is what I started with, interaction of light with small structures. What is a small? How do you? That is where the scaling starts here. So that's the material scaling. The bulk interaction, that means interaction of light with bulk materials is no, that's what happens. And the recent developments, you know that the miniaturization started somewhere in 1960s when the transistor was invented, and now we saw the last 50, 60 years of development in microelectronics. Today we are talking of nanoelectronics. All this have happened because we understood the physics and the chemistry or the properties of materials at when it is scaled down. So same thing is continued. The light interaction with when this material scaling is done, like interaction of light scattering due to a harmonically driven dipole oscillator that happens in the molecules. The physicists know this one, chemists, they understand this dipole moment driven dipole oscillator. So that happens in molecules in nanoparticles. Nanoparticles, it has been classified into insulators, semiconductors, and metals. Where an insulator, that's called the Rayleigh scattering. The semiconductor is resonance absorption. It's again the size dependent flow cells, which I showed in some slides before. Then metals, resonance absorption at surface plasmon frequency. See, these are the new terminologies. So when we talk about photonics, we talk about photons. Light has a dual nature. Okay, it's a wave as well as particle. It's a photon. But when you go to nanophotonics, we use a new terminology called plasmons. Okay, these are also a amount of energy, but their properties are entirely different. You cannot compare that with a photon properties. Okay, then microparticles with the dimension of the order of lambda or bigger. See, this is very important. Microparticles, molecules, and nanoparticles. The interaction of light with this is where the nanophotonics begins. Okay, so in microparticles with dimension of the order of lambda, many things can happen. Enhanced forward scattering, intuitive ray pictures, useful rainbows due to dispersion at H2O. That we know this one application, the resonators, lasers, and many of these have been understood, and a lot of device technologies have been developed, and this is moving towards nanoscale. Okay, now definition-wise, what is nano photonics? Nanophotonics or nano optics is the study of the behavior of light in the nanometer scale. Okay, and of the interaction of nanometer scale objects with light. So it's a branch of optics. In a way, optical engineering, physics, electrical engineering, and nanotechnology. That's why nanotechnology is multidisciplinary, and hence the nanophotonics. Okay, so everything has to be understood in a way where the fabrication, interaction with other disciplines, and understanding of the disciplines that involves nanophotonics. It is often, but not exclusively, involves metallic components, metal nanoparticles, which can transport and focus light via surface plasmons or surface plasmon polaritons. Okay, so this is how the nanophotonics. See, in general, we talk when the photonics we talk about it is from UV to mid-infrared, and here nanophotonics also in the same range, little bit of lesser, 300 nanometer, 1200 nanometer. Now, this is very important. About the plasmon, maybe this where I want to give an introduction on this one is the new terminology is coming here is the plasmon. I think plasmon is the density wave in an electron gas. It is analogous to sound wave, which the density wave in a gas consisting of molecules. Here, instead of molecules, we are talking about the electron gas. Okay, plasmons exist mainly in metals, where the electrons are weakly bound and free to roam around. The free electron is called the Jellium model. See, like in quantum mechanics is the one which made us to understand the phenomena at atomic and subatomic scales. And here also new models have been proposed. Though they are not the ultimate models which explain everything in nanophotonics, but some models are already there. It's a Jellium model provides a good approximation. The electrons in a metal can wobble like a piece of jelly, back and pulled back by the attraction of positive metal ions that they leave behind. I will show you the model which has been proposed. In contrast to the single electron wave function that we encountered already, plasmon is a collective wave. Okay, brilliance of electrons oscillate in synchronization. Okay, this is how the model is explained. It's a metal sphere, and this is a Jellium model. Okay, and the red circle is immobile positive charge distribution, metal. The right one is a free electron cloud, and when they interact, okay, pull back and forth, they create the Jellium on the right side. So this is how the plasma oscillation. So most of this light interaction with light materials at the nanoscale, they have been explained and the plasmon, they may not necessarily all, but there are many other physical phenomena that happen, and they have explained with different theories as well. But the most dominant one is this plasmons. Okay. Now another one is the surface plasmons, are the coherent delocalized electron oscillation that exist at the interface between any two materials. It is real. No, normally it is metal dielectric interface such as metal sheet or the air. Okay, I think I will show you that model. Okay, the charge motion in the surface plasmon always create an electromagnetic field outside as well as inside in the metal. The total excitation, including both charge motion and the associated electromagnetic field, is called either the surface plasmon polariton or planar or the localized surface plasmon. This is the model which is well accepted now. So bottom is the metal surface, that is the dielectric at the top, and then the light falls on. Okay, I think indicated by H nu. There is a charge created at the surface, positive and negative, and that's what the jelly model, and that creates the surface plasma. And the surface plasma energy decreases with the when you go away from the interface between the dielectric, and this is indicated here, and this is the model that's accepted. And I think many of these nano photonics phenomenon, interaction of light with nanoscale matter, is explained under this model. These waves can be excited very efficiently with the light in the visible range of the electromagnetic spectrum. Okay, this is very important. Most of this photonics, so for the visible, this one is used wavelength. So in the bulk metal surface and the metal sphere. So bulk metal also you can observe nanoplasmonic behavior. Okay, and I think the models have explained all these things. Metal surface where the metal surface plasmons, in the metal sphere nanoparticles. Okay, that surface plasmon polaritons. So this is how nanoparticles. Most of the people do a lot of metal nanoparticles, and see the light interaction and many various other applications. I will cover a few of them. This is how the plasmons are generated. It's a wave like it's like a sine wave, like similar to our electromagnetic wave. Here it is the middle, the top, the field on the surface. This is because bulk structure. And if you look at the electromagnetic spectrum, it is very common. And this is a wavelength range nanophotonics exploited like that. Now, why nanophotonics is you can do a lot of devices, still a lot of bottlenecks. I don't deny that part also. So normal optical components like lenses, microscope, objectives generally cannot focus light to nanometer scale, and because of the diffraction limit of light. This is all you know in a normal microscope. So you cannot increase the magnification beyond 100, 200, not beyond that. It's impossible. So you go to next range of magnification only through scanning electron microscope of TEM, tunneling electron microscope. This kind of higher and this thing, because you cannot focus the light. I mean, there's a diffraction, light diffraction. All basic physics, when light passes through the whole of the order of the wavelength, you see the diffraction. We are hitting the diffraction limit, so that is not possible. Now, nevertheless, it is possible to squeeze light into nanometer scale using other techniques. That's what I told you the concept now. Surface plasmons, localized surface plasmons around nanoscale metal objects, nanoscale apertures, okay, nanoscale sharp tips used in near field scanning, optical microscopy, and so on, and photo-assisted scanning, tunneling microscopy. See, so this is where the new opportunities started. Okay, and somehow some of them have been already realized and deployed. So this is very, very important. That means the nanophotonics is the one where we can really focus light into that nanometer scale and exploit the diffraction limit. That means across the diffraction limit and do a lot of other optical applications. Now, so these are the possible applications. Some have been realized. One is the communication technology. Lasers have been realized, though maybe may not be nanos photonics based lasers. I don't know whether commercially available. Solid state lighting, data storage, lithography. See, there is a. I think you all know lithography has a limit because of the light diffraction. We can go across that one. Use optical lithography to make real nanostructures. That's where some of these points I may cover in between. Biosensors, optical computers. This again, what field there? Solar cells. Some of the examples I can show you: displays, medical imaging, microscopy. A lot of applications can be realized with this nanophotonics. It is again a fusion of many disciplines like nanotechnology, photonics, plasmonics. I think so many things are covered here, and a lot of opportunities for research as well. Okay, and if you go here, conceptual view of nanophotonics as nanoscale optical science and technology. That's why people are talking about. One is, so if you want to really do nanophotonics, first you have to have a nanoscale confinement of radiation, nanoscale confinement of matter. Okay, that is nano structures, fabricate the nanostructures. Then confinement, so light interaction with the, that's again, I don't say it's a limit. There is a possibility you can do that one, and this you have to cross. Then nanoscale photoprocesses, that means try to understand the nanoscale photoprocesses, either plasmons theory, okay, that is called photochemistry at the nanoscale, okay. So these are the three things. First, confinement of the matter at nanoscale, then nanoscale confinement of electromagnetic wave, then try to understand. These are the important things. Now, length scale in photonics you can classify like this. Optical fiber, it's in the micron scale, and this is about kilometers long optical fibers we have today, tens of thousands of kilometers we can pull, and again we can make fibers, single mode fibers about 8 microns diameter, and still you can still see photonic crystal based fibers are still smaller than that. A lot of other advantages over there. 1 millimeter scale, you can do a lot of optical processes by fabricating integrated optical devices. 1 millimeter, a lot of things, and it's 10 microns. You know all how to make this on the silicon. Again, it's a photonic crystal structure on the right. This one right bottom here, of 1 micron is about 10 micron, almost equal to lambda. So this length scale structures for photonics, and I think I will skip all. These are all the things we can fabricate on silicon. Silicon photonics again, what we lot of nanophotonics can be done through silicon only because it's a well-established process technology. Better to follow that one. Photonics, electronics, okay, then plasmonics. These are the combinations you have to do for making. So this is again optical. These are all the well-known things, and okay, if you look at the bottom figure, this is an integrated optical device where pump signal, release and multiplier, optical amplifier, WTM, okay, SPL, surface plasmon, and signal converter. All these can be fabricated into a single silicon chip, integrated optical device, the one chip, 1 centimeter square chip. These are all things that you realize. Okay, this is basic way of John is because it is very much similar to electrical wires where you pass the current from one location to other location. The same way, where the light is propagating from one location to another location, the silicon chip. But to do that one, these waveguides are fabricated, and there are channel waveguides, and chip-loaded waveguides, and buried waveguides, and this similar waveguides, optical fiber, okay, and this all this can be fabricated on silicon. Now this is all integrated stuff. Is all this realize now varieties of materials are being used. This is how light can be made to propagate from one process processing location to another using this waveguides and photonics on silicon. This has been taken from the internet. They have been quite already. This is an ultimate target of all optical computers. You can do all using light only. I don't know when it will be right. Now coming back to this one, another important material for nanophotonics is this photonic crystal. Okay, this is in a way in semiconductor physics or electronics in the semiconductor where that is a band. It allows only electrons and certain the conduction band, balance band, and get to the conduction band. Same way we can.
Dr. Hegde. Dr. Hegde.
Semiconductor. Hello.
हाँ डॉक्टर हेगड़े थोड़ा वॉइस क्लियर नहीं आ रहा है, थोड़ा बैकग्राउंड नॉइज आ रहा है कुछ
अभी फिर एक मिनट हेलो
हेलो हाँ
अभी ठीक हो गया
अभी ठीक हो गया
अच्छा
हाँ ठीक है
अच्छा so this is okay. Photonic crystals are very much similar to semiconductors in electronics. So that's why it's called photonic crystals, semiconductors of light in a way. See, semiconductors have the periodic crystal lattice, and photonic crystals have periodic variation of dielectric constant. That's all. You can see the difference. The length scale is about 3 to 6 angstroms. The length scale is about lambda wavelength. So it is an artificial structure. These semiconductors are, that silicon, germanium, or whatever it is, they're all natural structures. So here, electromagnetic wave can be controlled by designing the periodicity of the dielectric material, that periodicity of the refractive index. That's what the periodic change, the refractive index can be made such that light can only certain wavelength can propagate through the that's what the photonic crystal is. So here these are all naturally available photonic crystals, okay, but you cannot make them the devices because their structures is entirely different. But you can fabricate these photonic crystals using silicon process, and you can make them to select a wavelength, and you can develop various other devices. This is a well-known field now. So this is how the photonic crystals, okay, can be made either in 1D, 2D, 3D. They're all available, and these are the naturally available photonic crystal structure. This is the structure on a butterfly wings. This is as a photonic crystal structure. So these are the one is making the nanostructures on a silicon. That's a starting point, and you can also use other techniques of nanofabrication to make structures to do the nanophotonics. Anyway, nanomaterials, enhanced surface, plasma and resonance sensors, these are all the things already realized now. The carbon nanotubes, silica nanoparticles, up-converting nanoparticles, quantum dots, magnetic nanoparticles, graphene, calcium phosphate nanoparticles, metallic nanoparticles, all these materials have been well established, studied now for nanophotonics applications. Okay, some of these, that's what I told you, to make up real nanophotonics, you need to have a nanostructures, either one of these, where another new materials are also coming, I don't say that. And these are the things that have been found applications in medicine and sensing and communication and various other devices. Now, one of the examples is this one, surface plasma guided light to the nanoscale. That's what guiding the light. And I think the same concept is there at the top. You put the nanostructure here. Here, I think this I have taken from some website. Okay, the light, there is a nanostructure here. Okay, and you launch the light here, guided to, and a new wavelength is coming out here because of the plasmonic effect. And this also some similar example, varieties of examples can be taken along. When you want to make anything at nanoscale, you need to follow the semiconductor processing. That is the, I don't say it's a bottleneck. Sometimes it is good, sometimes it is difficult because process is not that simple, and it is not like electronics device fabrication where you talk about maybe yield and etc. etc. But here it is very difficult because individual device has to be tested after separately. That means you have to test all this because launching the light is not possible as a bulk, but you can test the electronics device in bulk itself. So this is where the bottleneck is. And again, exciting surface plasma with an electron beam. This also, as I skip all these things, let us go to the fabrication part. So before doing any nanophotonics, important thing is fabricating the nanostructures specifically for nanophotonics applications. So the thin film deposition is still there, okay, but even though it is very simple, fabrication process, it's not good because you cannot really do nanostructures. You can make some thickness in one dimension you can do, but not on the 3-dimension. You can get a 3D structure for nanophotons. Clean room fabrication, that is very well-known technology, and that is where you can do a lot of nano structures for nanophotonics. Then optical lithography. This is also a well-known technique that is possible now. EV lithography, focused ion beam milling. These are the higher-end techniques. They are also being used. Okay. Then other techniques were colloidal self-assembly, biotemplating, chemical methods. These 3 methods are not that expensive. I think any lab can do. I think this I also prefer because for research point of view, these are the best methods to do that way. But when you go to for a research point of view, this okay. But when it comes to bulk, I think these techniques are better. So these are the techniques regularly used for fabricating nanostructures, specifically for nanophotonics. So I'm just focusing only for the nanophotonics part. So we may not go to all these things. Okay, very few I'll touch upon. So nanophotonics is truly multidisciplinary. That's what few examples I have given. Physics, first you need to understand the chemistry part of it, biology and biomedicine, engineering, all disciplines. Okay, so you have to do. Now I'll give some examples of microphotonics, micro optoelectromechanical systems where photonics plays a role. Then go to real nanophotonics. So these are well established now. In MEMS optical switch, a micromirror is used to reflect the light beam. So the direction the light beam is reflected can be changed by rotating the mirror. Different angles allowing the that can be moved in all direction. 3D mirrors around. This type of optical switch has been realized through the fusion of various techniques. Okay, so I can show you some of these mirror structures. Okay, so on the right corner you can see a optical micro mirror fabricated on a silicon. This silicon, mirror can be rotated in all 3 directions here. Okay, so allows compact low loss switches to be formed at any scale. Switching can be performed at hundreds of microseconds. Okay, this is very important, and this have been realized. Okay, This is where I showed you array of 3D micro mirrors fabricated on silicon in bulk. That is very important here. One mirror is moved here, other mirrors can be where this can be applied. That is applied is very important. These have been already deployed. Okay, MEMS based cross per 2D optical trunk switches. This is the input fiber. Okay, this is the optical mirror. Okay, micro mirrors, and the red mirrors are uh, off, and the green is on. So you can switch the optical signal from one fiber to the another fiber using these micrometers. Okay, this is one of the examples of microphotonics, and this is again a micromirror in sensors. You see, this is a schematic of a laser diode, a diode laser, and this is a micromirror, and this is a photodiode, and this is an actuated mirror, okay, connected to an actuator, a silicon. This can be fabricated, and this has been used as a accelerometer as well as a sensor. So this, I think, we have fabricated long back. Now if you look at this this entire structure on an optical table, this is by 6 feet by 3 feet, okay, and same thing is called as tunable external cavity semiconductor laser. This is where the structure is shown here. Okay, that is reduced to 6 inches by 3 inches now. The same thing, we modeled it, okay, forget about this one. Same thing is fabricated on a silicon. About the entire structure is about 200 microns by 50 microns, okay. This is a mirror, okay, this is, okay, and fabricated. This mirror can be folded up and down, and it can be moved back and forth like this here. This is a laser diode, this is a photo detector, and this entire device has been fabricated on silicon as microphotonics device, okay, a sensor, as an accelerometer. Now another example is this micro lenses. I think everybody knows this, where these micro lenses are sitting. Everybody is microphone is having these micro mirrors, okay, and these micro mirrors, okay, are fabricated on silicon. And I think I have some mirrors because one of my students immediately after his master's, he joined this company where they're making just micro mirrors. That time they used to make in a 10 micron. Today I think I don't know, maybe 1 micron mirrors they may be making it. These micro mirrors, you know that the capacities of mobile phone cameras, this they are almost equal to those olden days. What is it? Zoom cameras, okay, Nikon and bigger cameras. The same capacity today we can see. These are the microphotonics based devices. This may be around few microns, and today you can see even variable focal length micro lenses. Okay, these micro lenses, and this is realized. And then two waveguide based switches, and this you can see. This is also one of our old work. Entire thing was fabricated on silicon. By move the switch, you can see now this is an optical fiber, and this fiber is connected to this waveguide, okay, and the signal is transmitting from this way to this fiber. Now I can optically, okay, switch this signal to another fiber. Now you can see here this is connected to this waveguide and connected to this fiber. This is one of the models for the switching, optical switching using MOMS, micro optoelectromechanical systems. Okay, this has been realized. Okay, back this is very old work, of course. This model, same thing has been fabricated on silicon. Okay, see, these are all the individual components. Modeling has to be done. These are the actuators to move the switches back and forth. And I'm not going to the details of this one, how this has been designed, this and realized on silicon switch fabrication process. Okay, and you can see here these are the switches. These are the waveguides. This is the fiber connector here. These are the actuators here, and you can see the top view from here exactly whatever I have shown in the model. that has been realized on silicon. Okay, and many of such switches. Okay, this is one of the switches we showed, and varieties of switches people have done, and many have been converted into technology. Okay, now this is where the microphotonics, okay, or micro-optoelectromechanical systems we realize, and we have a overview of this microphotonics. Now, how the same thing has been extended for nano photonics in terms of application, because I think in the introduction itself I have talked about how this nanophotonics is evolved when the structure is reduced to nanoscale. Entire physics chemistry is different, and we need to design everything according to that. So now let us just glance about this one. Nanophotonics. Nano optomechanical system. Okay, nanophotonics is too broad. I'm just focusing on nano optomechanical system. To do this one, the important thing is the fabrication. Even for the previous also, we use all those standard fabrication processes where optical lithography, and deposition, this one plasma exchange, etching, required material, this one combined electron beam lithography and optical lithography. Okay. So this is one of the important things, the mask making. Okay. So this is a mask counter. It's also again optics device, laser based mask writers or laser writers. So we can use real mask using this. And then another one is a mask aligner to make the photometry. The transfer certain design patterns which are shown here. I can using this one can transfer. Then again one is LED. Then I'm not sure whether this material removal as well as etching is done in the position. They're all the standard techniques. So one of the important things is to do real scale, nanoscale. Photonics. You need to do some nanostructures. That real nanostructures can be really fabricated using this electron beam lithography. So it's a very complicated process, and not going to. You can go really make sub 10 nanometer minimum features and dimensions you can make using this one. Even electron we use in the position, 2 nanometer you can do. So electron beam induced etching also can be done. Nano manipulators, all these are combined in this instrumentation, very expensive. Real nanostructures can be understood or fabricated using this higher end. There are other techniques as well, and controlled this one can be done. This is at the same time it's an SCM as well. So you can do this one. Okay, I don't say that it's not possible. It's possible. I think it's a facility we have in IIT. I think many places we don't have, but for the IIT side, it will be totally facilities. Now, this is one example I show you here. Is the micro nanophotonics device. If you look at, I think everybody uses these days.
Dr. Hegde.
Atomic force microscope.
Sir, voice is a issue.
1 minute.
Can you keep your speaker thoda?
1 minute. 1 minute. I will try to do this one.
Yeah.
अभी ठीक हो गया?
A little better. Okay. Yeah. Okay.
So, if you look at,
you need to keep the microphone little away from your.
Okay.
Yeah. Okay. Or you are using two devices simultaneously now. So one speaker must be off.
Yeah, no. Maybe I have put both the headphone, this one together.
Yeah.
Maybe I can.
Yes.
Okay. Is it okay now?
Yeah, little
Hello?
better. Yes.
Ah,
Yes.
okay. So this is another example just to move forward. This is an atomic force microscope. It is again a micro nano photonics device in a way. You look at the cantilever, it's a micro electromechanical device, you know that. And the tip of this cantilever is very important. This atomic force microscope is used to study the surface of the material, nanoscale. Okay, this can give the surface roughness with a resolution of about 10 nanometer. To get that much of resolution, the tip has to be around 5 nanometer. The tip of this cantilever, you can see this one here. Okay, and this is in a way, it's a nano scale structure. This is a micro scale structure. On the top of it, you have a device. This is a laser beam. Okay, so here is a quadrant photodetector. When you scan this on the surface of this anything which you want to study, so there are two contact mode, non-contact. Okay, I'm not going to the details of the device. Only I'm trying to demonstrate that this is a micro nanophotonics device. So here is a laser beam. When you scan this tip from one end to the another end, depending upon the type of the mode of operation, this moves up and down at a resolution of 10 nanometer. That's all. So accordingly, this laser beam also will shift, and you collect this shift, light shift of this light from this location, and we can create the image using the computation and the technique. So it's a quadrant photo detector with whatever the light being shifted because of this movement can be recorded, and the surface can be projected. The surface roughness can be projected. This is the device, and it's well established in the technology is well known. Okay, this is atomic force microscopy where both MEMS norms, okay, MEMS norms, both are being utilized. Okay, this is very, and further it has been used for even lithography also, using the same tape in the contact mode. You use the right material, you can make varieties of nanophotonic structures. That means you pull the cantilever with a hose on the top of the this one. Okay, so this you apply the force on this one, pull the this one. You can make varieties of nanophotonic structure. This is very much similar to the flowing. Okay, very old technology, you know. So this is one of the devices which I just gave an example, and another example which I can show you here is real nanophotonics. I think this is one of our defense DRDO project which they gave to us to measure the very small force of 0.1 micronewton force. Can you develop a device for us? This is what they asked us to do. How to do this one? You cannot measure such a small force. This is even smaller than our breathing. You just breathe, the force which can create on a piece of paper if you hold it in front of your nose. So that is a very small force. Then we propose a device. This is a cantilever, and use some nanophotonics device. That means use the light for the measurement. So this cantilever, and we model that one. This is the standard way of fabricating the cantilever. We introduce a photonic crystal structure. Okay, this is a photonic crystal kind of hexagonal ring resonator. Okay, ring resonator structure to display high quality factor, high sensitivity. So we introduce this nanophotonics device at the neck of the cantilever. Okay, here you see here, and whatever the force is falling on this one, there is a shift in the wavelength, resonant wavelength. When you launch the light from this end, because of the force on this one, you can measure the light output from this waveguide here. So when we modeled, we saw that it's possible to measure the force. Okay, this is the wavelength shift, and we modeled this with 0.1 micronewton to 1 micrometer force applied. We saw this much of shift here. So this is a model. Whether it is really possible to fabricate that one, that was the challenge for us, and we started this project and we did it. And now we introduced this. This is the cantilever top view, and this is the photonic crystal structure. This is the monolithic. That means we fabricated photonic crystal structure. This entire thing is on a silicon. This is silicon cantilever we fabricated using optical lithography. Then we introduced this one using e-beam lithography and fabricated on the same cantilever. Okay, so these are the fabrication of force sensor, photonic crystal we fabricated, PC waveguide, resonated fabricated, cantilever we fabricated, and put together cantilever with photonic crystal, ring resonator, stick waveguide, tapered wave, see rating coupler, all these key components, because see this photonic crystal is about dimension also given here. So this is the photonic crystal. You can see periodic structure of hole and air gap. Okay, the solid structure and the air gap. Hole is air gap, and this is silicon oxide. And the diameter what we our model showed as a 240 nanometer. Diameter what we achieved is 254. It's okay. So we are within the range. So entire thing was fabricated on SOI wafer, and process flow was very difficult. And you see, you can make this structure, but launching light, again the challenge is to launch light into these waveguides is a very, so the entire structure is, this is about, I told you about 200 microns. Cantilever length is around, sorry, about, I'll give you somewhere here. Okay. Width is about 115 microns, length is about 50 microns, and thickness is 290. This one 200 nanometers. See, this structure is entirely about, total structure is altogether about 20 microns, maybe sorry, around 100 microns. Okay, 100 microns. This entire structure. This is when the photonic crystal is sitting here, and the waveguide light launching is from this location. So that is about see about 100 nanometer or 200 nanometer. So that was the challenge. And then we introduced this grating couplers over there, and all these things have been fabricated. Ultimately, we're able to measure the force. Okay, this is the top view of the ring resonator and the entire structure. This is the okay. We cannot cover all these things in one SEM image, so these are the split images. This is the waveguide coupler, and we also tried in this ring resonator planar waveguides. All the structures with the photonic crystal, we are able to measure. Okay, this is result what we measured. Okay, we are able to do all these things. We are measure. See, and ultimately the challenge was making it a package device. That we are not successful definitely, and we are able to measure up to 0.1. See, the measurement also was a challenge because how to you put it in a very isolated, even a wind won't show that much of force. See, this is a nanophotonics based device. Lot of fabrication challenges, lot of packaging challenges. You can fabricate and can measure the force of 0.1 micronewton, but the bottleneck is making the device into a deployable device. That's with the package, and that was the challenge. Okay, then later we change it to this kind of structures, and everywhere this is the problem. So this is one device we tried in the nanophotonic scale, and another one is it is not a clean based process. Metal ionized fluorescence on silver nano triangles. Again, this is a nanophotonics based device for fluorescence enhancement. So this I think we also did it some time back. So there was a problem for biologists. You know that for biology, for anything, first thing for any measurement is they go with a microscope, then with the fluorescence. So in some of the biomaterials are not highly fluorescent. If the fluorescence is below certain level, then you cannot measure. So one thing they want is the fluorescence enhancement. So that's what we started with. So is it possible to enhance the fluorescence using plasmonic effect? So is it possible to make the nanostructures, then put this this one, the biological weak fluorescent material on this nanostructure? Is it possible to enhance the fluorescence? That's what the problem started, and we are able to make such nanostructures, silver nano triangles, silver planar. Okay, I am not going to the details of these fabrication processes. You can use varieties of techniques to make silver nanoparticle these days, and this is where we consider this one as a nano triangle, and this we fabricated these nano triangles, okay, and using this atomic force microscope, we measured all these things, okay, 250 to 65 nanometer, 310 nanometer base, and later we put the biomaterials on the top of this nano triangles. Then we saw the fluorescence enhancement. Okay, this is where the fluorescence enhancement was observed. Okay, and about okay, uh, some here. Okay, this you can see. This is about 100 microns. We saw about how much? 15 to 20% enhancement of fluorescence, of weak fluorescing biological materials using these nanostructures. Okay, that's where we can use this nanophotonics in biology. One of the examples there are many, and then another one is, you see, this is a simple grating structure. In optics we regularly use these gratings, and first thing is we saw okay, simple grating, polymer gratings, okay, and polymers with 50 nanometers gold. So you can see this is a very clean grating structure. In e-beam lithography, we have certain limitations. So this is with the metal on the top of it. We saw a lot of scattering of the electron beam. Then this structure was very rough structure. We couldn't use it. So without that one, silver on a PMMA polymer, we got a very beautiful structures, and this has been used for the same purpose. One is you can put the biological samples. Say if you want to handle a single cell, it is very difficult. Cells can fold in any direction. If you put this biological samples, they will follow because their structure is of the same order of this periodic gratings. So they will follow the same structure, and you can see even enhancement, fluorescence enhancement as well. Okay, this is where the grating structures we got, and varieties of such nanostructures can be fabricated, and a lot of biology application now can be realized. So this is again a nano grating. Okay, you can see these structures. This is a very beautiful cell structure. This cell is following this nanograting structure, and you launch the light, you can see varieties of fluorescent images. You can do a lot of studies of this. This again a nanophotonics application. And another application which we explored was in photovoltaics. Photovoltaics, I think, so again, very interesting field. Is part of photonics in a way, I can say. In photovoltaics, ultimate goal is to enhance the efficiency, and varieties of materials are. One is, silicon is the ultimate material. People know that as established, and as ultimate material. People are thinking, we cannot further increase the efficiency in silicon. So people are looking for other materials, and you can do something with even silicon also. So ultimate goal is to see that whatever the photon falls on any photovoltaic solar cell material, each photon should be utilized. You should not use any photon which goes into the solar cell. That's the ultimate goal. to achieve that one, varieties of techniques and of fabrication methods have been explored, varieties of materials are being explored, and still it is the same. In silicon, also people are still working to enhance the efficiency. And another challenge is to make a simple process and a large area silicon synthesis, silicon solar cell. That is another area. So we started introducing some nano, for nano pillars, nano rods, varieties of nanostructures. First we modeled this one, and we realized that there is no enhancement in the efficiency if you just introduce some random nanostructure in a phototype for charge collection, or charge separation, or whatever it is. And that I think we published that one in applied physics. We initially said that it's impossible to enhance the efficiency by just introducing nanostructures in the photovoltaic cell. And that is the model we published. Then we realized instead of using random nanostructures, if you use some nano optical components, okay, either nanoscale lens or nanoscale mirrors, this kind of structure. If you are able to introduce such structures in the photovoltaics, then is it possible to improve the either in one of them, not necessarily that just efficient. Ultimate goal is efficiency, but how to do that one, introduce that one, that was the challenge. So we started moldable biometric nanoscale optoelectric platforms for photovoltaics. This is what we started. We looked at the insects in the mosquitoes and the fruit flies. They all have some kind of nanostructures in their eyes, but these have a close look, the same images. We saw, because even mosquitoes can identify identify us in a very, very dark atmosphere. This one, even single photons they can detect the person is here. That means the photons, that means definitely the photons they will catch. These kind of nanostructures we observe, and we tried. This is actually in a way it's a nanoscale lens, and this is our model. Whether if we introduce, this is a planar photovoltaic cell, okay, plane surfaces you can see. This is a modified structure. This modified structure is nothing but a nanophotonic structure. This is an active layer, bulk metal, okay, whole transport, charge collection. So when we introduce this structure, this is the light we first modeled. We saw that when this photon enters here, this is a plane surface model. This is a model with some nanophotonic structures introduced. First, when we saw this one, we saw that there is minimum reflection light. When the light goes inside each layers, no photon, the minimum photons are lost, and each of these photons are being used in charge generation. And this one, we use a lot of scattering, reflection, loss of photons on this one. Then, and we realized this one, then we got into these structures. Is it possible to make this? Is at the nanoscale we remove model. Then we saw this one and we started fabricating this one. So I think I have shown in my nanofluorescence enhancement in biological structures. So this is similar fabrication process which follow, and we made these nanostructures. Okay, these are the non-clean room based process. That is another important thing. We don't want to go to clean room for all process. That is very, very long and very, very complicated. We did it in a simple laboratory and use this polystyrene sphere based process. This is about 300 nanometer diameter of polystyrene spheres. We introduce and made these structures. Okay, it's a 1 inch square. This one. This is the nanostructure made, and this is the planar structure. You see, there is a beautiful grating effect. We observed this one. Then on the silicon, we made this template, and we did all the photovoltaic structures, whatever we wanted to do, and we saw a broadband enhancement in the external quantum efficiency. About increase was about 47%. You see, this is the planar structure, and this is the structure. Okay, nanophotonic structures. That means it's a lens structure. At the same time, current density was also increased in a structured one compared to the planar one. So what we observed was an improvement in the photocurrent up to 35%, enhancement in quantum efficiency is 47%, and overall we saw an increase of about 40% efficiency in the by introducing nanostructure in a photovoltaics device. I think this was published in 2018 nanoscale. I think we are working on a large scale production. We are trying to develop among with Bharat Electronic BL and make a large area solar cells. Okay, this is where the real nanophotonic application. Hello, some noise coming.
Yes,
Hello?
little noise was there, but now
Okay. Okay. So this is what we observed by introducing nano photonics in photovoltaics. Okay. So we observed a very good enhancement in efficiency, photocurrent, minimum reflection. You can see a broadband deep in specular reflection, and you can see how broadband light is going in a nano structured photovoltaic cell, and each of these photons are coming back within the structure. There is minimum loss, and you can see reflection as planar is specular reflection is minimum, structured is higher, diffuse reflectance. All whatever we saw in the model simulation, almost all realized in the real experiment, and we introduced, I think we have had a patent for this one as well. And okay, all this is possible with nanophotonics. Okay, so as I told in the beginning, we are trying to make it a large area based silicon solar cell by introducing the nanostructure. Now, in another important field is the introducing nanophotonics in microfluidics. Okay, so plasma effect of nanoparticles on biological cells is well understood, and another hot field is this microfluidics, where people are using a lot of photonics devices for in situ measurements, imaging of lot of biological phenomena that is taking place. Okay, so lot of I told you drug delivery, imaging, detection of various things. The only thing is, the microfluidics is also in a similar way. I think many people are working in that area. When the fluid is flowing in a very small channel, the properties will change, and that has been exploited for various biological and medical applications. So now you introduce this metal nanoparticles in the microfluidic channel and put the light on these nano particles. You see a lot of plasmonic effect, and further it affects the fluorescence, and you can also see other kind of property changes of the biological materials in this. Now, so sensing and diagnostic applications is the main in microfluidics, particularly when you go into the microfluidics and biological applications. Okay, so each cell membrane has specific biomarkers. Signature biomarkers varied from healthy and sickle cells, and our idea was to do cell lysing. Okay, this is one application. There are various other applications people are looking at, and then functionalized nanoparticle target specific biomarkers diagnosis of disease through attaching functional nanoparticle. All when you put these nanoparticles, ultimately it is the photonics devices. Ultimately it leads into photonics measurements. You have to launch a light. Just nanoparticles will not do much over there. Either you have to detect it, either you have to sense it, or you have to image by various other things. Then you exploit for various other things. Okay, so I don't know much about this biology, and this is where the microfluidic device which we fabricated. It's a very simple microfluidic device fabricated using silicon process, and this is the micro channel, and this is a photo detector, and this is the optical fiber. This is a laser light source, and this is the the nanoparticles, okay, gold or silver nanoparticles, and the sample is a biological sample. It's already filled with nanoparticles with different dimension. Okay, then the flow is going from here. You launch a light, you image from the top. Okay, this is imaging, and you can detect using the photo detector the wavelength or shift or whatever it is. Fluorescence imaging can be done from the top. See, what I'm telling is you can do a lot of nanophotonic based measurements simultaneously in situ using nanophotonics techniques. Okay, that is where the role of nanophotonics in microfluidics. Okay, so understanding the mechanism of the interaction between gold nanoparticles and biological cell membrane with exposure to low energy lasers. See, this is again, you have to be very careful when you are using laser light. Okay, focused laser light will kill all the cells or biological samples. You have to be very careful here. And for our application, what our objective was to do cell lysing, controlled cell lysing. That means cell lysing is cut open the cells and okay, healthy ones and diseased ones. So you can do a lot of studies. We are collaborating with biochemistry and doctors. So our objective was to make this cell and introduce nanophotons into this one. So cell lysing. That means one is you can use electric field to cut open the cell, but it is not controlled. You can use even optically. That means use optical techniques to cut open the cell. But if you have 100 cells, see, cutting the cell carefully, it's very difficult because cells will rupture. What you want is the cell constituent inside the cell. What is the mitochondria, DNA, RNA, all these components they want it later. So you want to carefully cut open cell and get the cell constituents inside as it is for further studies. That's what the biologists, medical doctors, they wanted. So doing this one in microfluidic cell in a controlled manner is very difficult. When we started, we used to cut open all the cells randomly, and we never used to get the components what they wanted. Then, so we realized, and the nanophotonics is the best techniques to do all these things, introduce nanoparticles, optical cell lysing. I think our yield of getting the right constituents outside, and it was successful, and we are able to do that one. Okay, this was done. Sorry, I think I am closing here itself. So some results are still yet to come. So in a controlled manner, you can do all cell lysing or other diagnosis processes simultaneously detecting, imaging, and separating the constituent. That's another important technique. Technique is here when constituents come here. There are various other ways to separate the ribosomes, mitochondria, DNA, RNA. All can be separated, and we can do other studies. So when you separate it, you should be able to identify whether separated is this one, this one, this one, this one. All can be done through optical imaging or the other detecting technique, introducing nanophotonics into it. So this is where, so nanophotonics has various applications, few which we have been trying to, that I have been trying to show all through this talk. I think with this one I will stop here. Maybe I think we have started bit early. That's why we are closing it bit early. Yeah. So I will summarize as it is. An overview of micro nanophotonics. That's what I wanted to give. And nanophotonics and nanotechnology cover many different areas, but one key set of methods for both is nanofabrication, packaging, measurement. Still, many bottlenecks are here, but I think definitely one day we overcome all this and we'll be able to see. It's a very interesting field of research. And a brief introduction nanophotonics-based devices of the future is provided. Few results of our related research work is also shown. There will be many opportunities for the industries to explore the application of unconventional photonics in many areas. I think a lot of possibilities are available, and the youngsters can do a lot of things here, and some of the research part of the papers here. And this is the clean room which I wanted to show we have at IISc. With this, I thank you all for your attention. I think if you have any questions, you can ask. Hello.
Thank you, Dr. Hegde, for the wonderful talk. As we have entering into the era of sensors, and so your talk on sensing and diagnosis, particularly nanophotonics in different areas, photovoltaics and microfluids, and we have young faculty and the fresh researchers. So you have exposed them to much of the terminology in the area of nanophotonics, and they can decide to work in this area. So this talk must be useful for the freshers, particularly the research scholars who are looking for the newest problems. Maybe some of the participants must have joined for getting the certificate, but it is not so. They have been given they have been given the glimpse of this nanophotonics area, that how important this area is nowadays when we are passing through the bad phase of our life, particularly the COVID-19, and we have to deal with the viruses and all that. So modern urbanization has given us this disease. I must tell you, this is all because of the modern evolved urbanization. Which have given us this disease, and we have now to deal with it, and we have to go a long way, and nanophotonics will be definitely a solution for all these problems to solve them. So your particular message, merging of the optics and electronics, requires nanophotonics. So your talk was quite impressive, so I thank you very much, and I hope that the participants have some questions in their mind. May I ask any one or two questions? If anybody is interested, he can give in the chat box, or maybe we can interact with you afterwards also. And you are in very well contact with us, and I know your nature, that you are quite cooperative, and anyone who would like to come to your laboratory, he can visit you, he can discuss with you, even on telephone, or even visiting your laboratory. Even I myself is thinking of coming to you.
Welcome.
So due to certain constraints and our hectic schedules, we cannot come sometimes, but we are close enough that we can discuss many things. So thank you.
Dr. Devan, actually this is it is not a very effective mode of interaction anyhow, but we have to live with it. No other way. And we are the creators of this virus, and we have to live with it. We have to cross all this. And what
we have to find out the solutions also.
And what my whole objective was to say that you need not have to wait for the bigger facilities to come to do some research. You can do with whatever is available. That's what I wanted to see. Non-clean room based nanophotonics device making or the structure making, that's also possible. So I'm very happy to interact or collaborate with anything which See, my whole idea was to do something simple, not going for something big without any plan. So I think you have all opportunities to do any questions you can ask, and if you want to have any a future interaction, or you want to use the facilities, all are welcome. Or you want to start anything in your university, also we are ready to help. Open. So it's all yours.
I must compliment, if some genuine participant is there, they may visit and they may work there and they may interact, they may discuss.
Yeah, sure,
I
sure.
definitely would like to encourage the genuine researcher who would like to work in the area of nanophotonics.
Yeah, yeah.
Okay.
So this is multidisciplinary, as I mentioned, anybody can. You come out with your own ideas, you're welcome. You're welcome.
One
And
Dr. Rajesh Thakur is there with us, who works in the area of bio nano, and we have a good collaboration with him, and he may.
Yes, sir.
Yeah, sure. Welcome.
Yeah.
Welcome.
Yeah.
So we also learn from you. A lot of things we can learn from you.
Yes, certainly, sir. It will be very nice.
Yeah.
We shall interact after
sure.
this workshop, and we shall look forward whatever we can do jointly.
Yeah, you note my email, phone number, whatever it is.
Everything is available on your net. Available. We have all communication, established communication. Don't.
Okay.
Okay. Okay. Thank you very much, sir. Thank you very much.
Thank you.
And it is for the information of all participants now that the next session will be starting at 3 p.m. So all may have the virtual tea as well as lunch at their places, and we will be meeting at 3. Dr. Hegde, your tea is pending. So whenever we will meet, it will be from our side, from GJUST.
Okay.
Right, okay. Thank you. So participants to report at 3 on the same link, and we'll try to put the lecture on YouTube as well. So let us see how the things go on the virtual platform. Okay, thank you. Each one.